Okay, so we have a question here, which is, let's talk about the 4Cs. When the memory block is in the process P0 cache and then gets read for the first time, is this a miss? Oh, if it gets read for the first time by another processor, is that a miss? It is a miss. Is this a compulsory miss? Yes, it is. So the reason why it's a compulsory miss is because something is a compulsory miss when it has never been in that particular cache. So for the level 1 cache, I mean, if we have a multiple levels of caches basically, and the level 1 cache is private to each particular processor, then if we miss on some block B in each of the cores, each time this is a miss in the level 0 cache. I mean, in the level 1 cache. And then if we have, for example, also a private level 2 cache, then that's also, separate misses in each of these caches. If we have a shared level 2 cache, then that particular miss will be a compulsory miss only once, just because basically once the first core creates a miss in level 2, that block has been in that cache. So every miss after that is not a compulsory miss because the block has been in that cache. So essentially, something is a compulsory miss for a particular cache when that particular block has never been in that cache before. The idea is that it's compulsory because you cannot hit on it if it's never been there. This, of course, assumes that there is no prefetching or anything else, because you can theoretically, you can have a hit even on a block you've never seen before if you somehow manage to prefetch it. But let's kind of ignore, for the 4Cs and stuff like that, we kind of ignore prefetching. So basically what prefetching can do is kind of convert a miss into a hit, but if it is a miss and it's never been in the cache, that would be a compulsory miss. Something becomes a coherence miss when it was in the cache and it would still be there, except that it's been accessed by another processor, and because of that we had to remove it. So again, it requires, again, it's a coherence miss for a particular cache, right? So for example, if level 1 caches are kept coherent, then when we have an access on, let's say, P1, it would be a coherence miss for the level 1 cache of P1 if P1 had it in the cache and it would not have been replaced except for a coherence action by some other core. So basically it becomes a coherence miss essentially only when I somehow fetch it into that particular cache. Let's say P1 has accessed it, and then what happens is, let's say P0 accesses it, let's say writes to it, and because of that we had to invalidate the copy in P1, and because of that now P1, when it next accesses it, will have a coherence miss. So essentially, to have a coherence miss, the block has to be accessed by that particular core, and then by some other core in a way that invalidates or downgrades the copy in the first core, and then it's again accessed by the original core. I'm not sure if that's clear, but that's pretty much it. Is invalidating the same as removing from the local cache? Well, yes and no. It's equivalent to it in the sense that when a block has been invalidated, and remember, like, block is invalidated when another core writes to it. Okay, so pretty much I have something in my cache, another core writes to that particular block, and because of that, in my cache now I need to mark this block as invalid, which makes the block behave exactly like not being there. But the block is actually still there. The block is essentially still occupying space in my cache just because it's just been marked as you cannot access it. So pretty much I will have to refetch it as if it wasn't there. And that's the kind of only difference, that basically, unlike all of the other misses, a coherence miss finds the block in the cache but cannot use it. Whereas for all the other misses, basically we don't have a block in the cache. So it's pretty much equivalent in terms of what we have to do. It's equivalent to removing it from the cache, except that the block is not physically removed at that point. It's just marked as inaccessible. In the simulator, it's not equivalent to this. So basically, in the simulator, okay. So the problem with marking the block as removed and then just doing that is that the real hardware will basically check whether it has a hit on the block by checking whether the tag matches and also whether the state allows the particular access to happen. So essentially, if something is invalid, meaning it's been invalidated, what will happen in real hardware is that the tag will match because the block is physically still present in the cache and the tag has not been messed with. So basically, the tag still matches, but the state is invalid, which means that because both of the conditions are not satisfied, we will not be able to actually use that block for reading, let's say. In the simulator, now the reason the hardware has no problem with doing that is that basically the check for the tag match and the check for the state match, as in is the state one that allows reading, are done concurrently. So pretty much there is no advantage to marking the tag as let's say 0 or something and preventing it from matching. So it's totally okay for the tag to match because whether the tag matches or not doesn't have any impact on how fast we can hit. However, in the simulator, because it's a software thing, what happens is essentially that if the tag, I mean, what we do is we basically first check the tag. And the reason we first check the tag is just it's an optimization of the simulator. So basically, we have to check both the state and the tag. We check the tag first because if the block is not actually present, the tag has a much lower chance of matching just because there is a lot of tags, right? So essentially what happens in the simulator, we first check the tag, and if the tag doesn't match, then we don't have to check for the state, which kind of speeds up the check for a miss. And then for if the tag does match, then we will still check the state. But the idea is that for a block that is actually not in the cache, chances are we will find that it just doesn't match any of the tags. We don't have to check the state. When the block is invalidated, the normal procedure that kind of mimics what the hardware is doing is essentially just change the state, leave the tag alone. Right, but for performance optimization reasons, I mean, what that would do is basically the tag would match, which would trigger the check of the state, which takes more time. And to speed up the simulator, essentially, the designers of the simulator chose to pretty much when we invalidate something, not only do we mark it as invalid, we also zero out the tag. And the idea is that way, the miss on something that has been invalidated happens faster because the tag will not match, because a 0 tag doesn't match what we're really looking for. Unfortunately for our project 3, that creates a problem because we cannot. I mean, what this does is essentially prevents us from really simply matching whether the thing is a coherence miss or not. Because normally what we would do is we would say, okay, if the thing is in an invalid state but has a matching tag, then we are having a coherence miss. However, because the tag gets zeroed out on an invalidation, the tag will never match if you have a coherence miss. So what you have to do is you have to, I mean, for the project, pretty much, if you want to do checks that way, what you have to do is essentially remember what was in the tag prior to its being zeroed out. So essentially, when there is an invalidation, we need to allow the simulator tag to be zeroed out. But then what you want to do is maintain kind of like add a variable to the cache block so that you can maintain what the tag was. So pretty much you can kind of have like a shadow tag that essentially is updated every time the normal tag is updated, except when the real tag is zeroed out, then your shadow tag would not be zeroed out, so that in the situation where we have an invalidation, you still have the original tag and you can check whether that tag matches what we are looking for. The reason you don't want to mess with the simulator's original tag is that once the designers had this tag being zeroed out, they basically in a lot of places kind of depend on the tag not matching when we're having a miss, which means that if you change it so that it's not zeroed out, it's going to create all sorts of problems in the simulator, and you really don't want to be dealing with all the places where the tag might be consulted. This way you're kind of just saying, okay, this, I mean, whatever that is happening to the tag, I'm just going to make it happen to my tag too, except if a 0 is being written to the tag, then I'm going to just leave my tag alone and not zero it out. but that allows the simulator to still see exactly the same kind of tag behavior that the code is designed to work with. So there are reasons why the simulator was done that way. I mean, it's kind of just cheating a little bit in terms of how it mimics the state of the hardware. And normally in a coherence protocol, this cheating doesn't really impact anything, just because it doesn't really matter whether you zero out the tag or not from the perspective of whether you have a hit or a miss. But because it speeds up the simulation itself, essentially the simulator has less work to do, they chose to do that. And the only thing that it impacts is this basically no longer models the fact that the tag is actually still present in the cache when you have a coherence miss. Okay, so glad to help. Thank you. Okay, so the question here is essentially what can we do with the simulator? And I mean, the answer is pretty much like the intent, like what the simulator was designed for, is essentially it was designed to allow you to experiment with the what we call architectural changes and the micro architectural changes, which means basically if you want to change, for example, how the scheduler of the instructions works, or if you want to try out a new branch predictor, like you come up with a way of predicting, branches, let's say, and you want to check whether it's, that it's good, as in whether it actually predicts branches better than some of the other ones, and also whether it actually leads to performance improvement. Then what you do is you basically kind of replace the branch predictor code with whatever is modeling your branch predictor, and do that. Same thing with if you want to change scheduling of instructions, or if you want to change, for example, which coherence protocol you're using and stuff like that. So and the reason why the simulator is so complicated and has so many moving pieces and stuff like that is precisely because it allows you to do experimentation in all of these things. Now, the level of detail that you need in a simulator is basically for every part of the simulated hardware, the level of detail that you need for in the simulation of that particular part of the simulator is kind of proportional to whether to kind of at what level of detail are you making the changes. So for example, if you don't really care how the coherence protocol works, you can implement a relatively trivial coherence protocol that just keeps kind of the overall state of who has what at what time, but doesn't really model all of the which state am I in, and what happens when let's say two writes happen nearly simultaneously. So